Yo, what's up, Sci-Fam? It's your boy, Nickel, and today we're going to be learning about planetary airflow. If we look at how we're going to organize the page, we're going to first look at different types of air cells that form above our Earth's surface. Talk about the trends in the rising air and the sinking air, and then we'll also discuss the Coriolis effect. All right, let's jump right in. So in terms of how air moves across our planet, as the sun hits our planet, our planet called the water planet or the blue planet, all of that energy heats up the water on our Earth. When water heats up, water evaporates. So we're going to discuss what happens as the sun's heat instigates the airflow on our planet. So to begin with here, we're going to record just this general idea that different parts of the Earth heat up more or less depending on the angle of the sun. So the areas that are more direct sunlight heat up more. The areas with less direct sunlight heat up less. What this means then is that the equator receives the most direct solar radiation. And since the Earth is a curved sphere, the poles are at a different angle in relation to the sun, meaning that they don't get direct sunlight. They receive the least direct sunlight. All right, so in class we've done some experiments in order to demonstrate that and to prove that point. But let's look at how that affects the airflow. So you can see this diagram that I drew over here of the air rising up. When air rises, it rises because we have moisture on the ground that gains energy and that warm air rises. That's how hot air balloons work, is that hot air is less dense and so it rises up in the sky. Once it cools though, I made the blue arrow here to show that the air then cools down, and as it cools, it starts to then descend back down to the ground, where then it moves back towards this area where there's like an upwelling of air, and so this air, when it sinks, it goes to fill that space. As it goes to fill that space, it heats back up, and so we end up having this cycle happen. All right, so the area with the most direct sunlight is our equator. Let's label our equator. You need to draw yourself a circle here with some different lines. First, we need the equator. That's right there in the middle. Then just above the equator is an area known as 30 degrees north latitude. Above that, another 30 degrees would be 60 degrees north latitude. And then our poles are at 90 degrees north latitude. And this here would be considered our north pole. Well, the way the latitude works is that it's the same in the south, except for instead of north, it would be south. So the line directly below the equator would be 30 degrees south, and then 60 degrees south, and then the pole is 90 degrees south, or our south pole. All right, so since the equator receives the most amount of heat, let me get a different color here to show that we're going to have, and I'll use the orange since that's what I have over here on the left, is that since the sun hits the equator, then warm air rises up. It's going to rise up and it's going to fall both directions. Some air will move towards the north pole and some will move towards the south pole. Now, the opposite is true in that when we have really cold air, the area with the least amount of solar radiation is our poles. So at the poles, we're going to have air descending down. All right, well, what happens is that let's first look at the North Pole. As the North Pole air descends down to the ground, it then starts to move down the surface of the Earth, and as it moves further and further down the surface of the Earth, it starts to heat up. And as that air heats up, then we have rising happening here, and so we end up creating this little kind of air cell. That's what we call it. We call it a cell. Now, down here at the South Pole, the same thing happens, that when cold air descends, it then moves towards the equator, and as it moves towards the equator, it starts to heat up, and as it heats up, it rises, and when it rises, it goes up toward the North Pole or the South Pole where it cools, and then it descends back down towards the pole. Now the air at the equator, if we go back to that air was heating up. And as it heats up and it rises, it gets rid of the heat, it loses its heat, it gets rid of the moisture, and then that air cell actually starts to the air in this cell starts to descend. And as it descends then, it gets sucked back towards the area where the air is rising at the equator. So this happens both north of the equator and south of the equator. Now in between these two cells, you can see that on one side we have an up area, on the other side we have a down area. Let's get a color that's different than these two. So we can see that we're going to have a flow of air moving, where we have up direction of air here at 60 degrees north, and then that air rises, it cools, and actually moves towards the equator, falls back down, and creates this in-between type of cycle. But you can see that it fits in here, and so it's basically like some gears that are churning. Now each of these gears here on above the surface of our Earth, we have 3 air cells that are spanning about 30 degrees of latitude in the north, and also 3 in the south. The furthest north, the cell in the furthest north here, this one is called a polar cell because it's at the very top. And so this one down here is also a polar cell. The one below the polar cell, this one is called a feral cell. And the one down here that's in purple is also a feral cell. And then the cell here right at the equator is known as a Hadley cell. And so this one also is a Hadley cell. Now the reason this happens is because we have differential heating at different latitudes on our Earth. That as you go further north, there's less direct sunlight. At the equator is the most direct, so that's where air rises. All right, so when we have rising air, in this picture I kind of showed that you can get more storm clouds in that region. And that's because we have air that is going to contain a lot of moisture. So we have moist air. When air rises, it's typically pretty moist, and as it rises higher and higher, it cools, condenses, and we have forms condense from that process of air rising, of warm, moist air rising. We have cloud formation. So that also means that we end up with high amounts of precipitation. More clouds means more rain. And if we have more precipitation, then that means we have more vegetation. All right, if we have more vegetation and more precipitation, we have certain climates and ecosystems that we have certain words for the ecosystems that have high precipitation and lots of vegetation. A lot of times these are our rainforests. So let's take a look. Rising air happens here at the equator, and if we look at the equator, that's where a lot of rainforests are located. Up here at 60 degrees also, there are actually technically rainforests up there as well. If you've ever been to the state of Washington, you may have been out to the Olympic Peninsula, and that area is typically considered a rainforest, as well as some areas in British Columbia and up in northern Canada are considered a rainforest, and that's because there's tons of precipitation from that rising air. Well, what about these areas in between? Let's use a brown color actually. So this brown color here at 30 degrees, we have descending air, or air that is sinking at both of these locations. So if we have falling, or we can put in parentheses here, sinking air, we have the opposite. So it's not moist anymore because there's not much moisture in the air anymore. It's now been dried out. So here in these locations where air descends, it's because the air is dry. Also, if the air is dry, we're not going to have very much precipitation. So we'll have low precipitation because we have a lot of dry air. And if there's low precipitation, there's not a lot of water. It means that we're not going to have as much plant life. So we're going to have less vegetation. So areas where there's low precipitation and less vegetation are typically areas that we call our deserts. And so actually, if you look at a globe, almost all of our deserts are located here at 30 degrees north or at 30 degrees south. But there's another area the air is descending, and that's in the South Pole and in the North Pole. And actually, Antarctica, which is down here on the South Pole, is considered to be one of the driest places on Earth, meaning that it is our largest desert, is actually Antarctica. Even though it's all snow, it doesn't snow very much, very often, and so it's still considered a desert, actually. And that's because there's all of that sinking air. There's not a lot of moisture in the air. Well, that's how air moves in a vertical sense above our heads here on the surface of the Earth. But we're going to look at how air also moves in a different sense, meaning how it moves across the surface of our Earth. In order to understand this a little bit better, I'm going to teach you about a concept known as the Coriolis Effect. So, the Coriolis Effect, if you've ever been in a circle with people and you all held hands, and this circle of people started spinning around, this person in the middle doesn't have to spin very hard or very fast in order to do one rotation, whereas this person on the outside, if they want to keep holding hands with this person, with all the people connected to the inside person, they have to travel much further around to get back to their starting position, whereas that middle person doesn't have to move very much. Now, what that means then is that our equator of our Earth, since it's this wider part, is actually moving faster than our poles do. Our poles don't move as fast because it's like the center person here in a circle that's spinning. All right, so what all of this means then is that air is actually deflected as it travels from the equator, where it rises, towards the poles. So it's deflected, and that's because the poles spin slower than the equator. So what we see is that if air leaves the equator headed north, it actually moves in the direction from left to right in both the northern hemisphere and the southern hemisphere. Now the Earth is rotating from the west to the east. So the direction that this is orbiting is going in this direction. And then when storms or air leaves, it goes from this area in the equator, the western area of the equator, up to a more easterly position. Same in the southern hemisphere. It starts in a western area and goes to an eastern position. Now what that means then is we can predict that the weather in the United States, at least, is typically going to be coming from west to east, and also in the southern hemisphere goes from west to east. But if we look at how storms start to form, is that as that air moves north in the northern hemisphere, is that air, as it moves north, it begins to create this direction of spin. So if we have a hurricane in the northern hemisphere, we typically see it has a counterclockwise direction. In the southern hemisphere, if we have a storm or a hurricane form, it's typically called a cyclone, and this one is going to move in a clockwise direction. So actually, storms spin in opposite directions, whether you're in the northern hemisphere or the southern hemisphere, and it has to do with the Coriolis effect. It's the idea that as you travel from the equator towards the poles, since the speed of the spin is actually different because of the curvature of the Earth, then it actually causes air to not be able to move in a straight line. It moves in a curved path. And that curved path that we see is in this direction here, and it creates opposite rotations for storms, whether you're in the northern hemisphere or the southern hemisphere. So this contributes to patterns that we see in our weather, either on the surface from the Coriolis effect or in the vertical area above our heads, based on this idea of the different air cells that form here on our Earth based on the differential heating at different latitudes. And that is our planetary airflow.